Hi everyone, I welcome you to today's lesson. In today's lesson, we want to look at a basic concept in calculus called differentiation. However, we are going to look at one particular definition for differentiation. That is the differentiation using first principles. Now, anytime we use the formal definition for differentiation, which says the limit as h approaches 0 of f of x plus h minus f of x all on h, anytime we use this particular definition to evaluate the derivatives of functions, we call that process differentiation by first principles. So basically, we are going to use this concept here, or this definition, to evaluate the derivatives of functions. However, I am only going to look at some special types of functions. For example, I'm going to look at the derivative of f of x equals sine x. Then I'll do one for the exponential function and then the power function. Alright, so we want to find f prime of x using first principles. So we use the formal definition, limit as h approaches 0, f of x plus h minus f of x all on h. Alright, let me scroll up. Okay, so this is going to be the limit as h approaches 0. You know, f of x plus h means that if I have sine x, or if I have a function of x, then wherever I see x, I'm going to put x plus h there. So my function, which is sine x, is going to be sine into bracket x plus h minus f of x, which is sine x, all on h. Now this sine x plus h double angle, there is a trig identity for sine x plus h, which goes like, so we can write sine x plus h as sine x cos h plus sine h cos x. So in place of sine x plus h, I'm going to put this identity there. So the numerator is going to be the limit as h approaches 0. So sine x cos h plus sine h cos x minus sine x all over h. Now look at something. Look at this term and then the last term here. They both have sine x. So I'm going to factor sine x out. And if I do that, I'm going to have sine x out. Then I'll be having cos h minus 1 plus cos x and then sine h all over h. Alright, now look at something. Because we are taking the limit as h approaches 0, any other term without the h is treated as a constant, which can be factored out, right? But before I factor out those constants, I'm going to break this limit into two. So the limit as h approaches 0 of sine x, then we have cos h minus 1 all over h, plus the limit as h approaches 0 of cos x, then multiplying sine h. So I've just splitted the limits. Because they are adding, I can take the limit of each term. Then from each of these, the ones without the h, I'm going to factor them. I treat them as constants. So sine x will come out. Then I'll have the limit as h approaches 0 of cos h minus 1 all over h. Then plus here, I'm going to factor out cos x, right? I'm factoring the ones without the h. So cos x, then I have the limit as h approaches 0 of sine h on h. Now look at these limits, these particular ones, these particular limits. We have some special limit in trig. Now this particular limit is a special limit in trig, which says, let me write it here, the limit as h approaches 0 of cos h minus 1 over h, that limit is 0, right? Then the limit as h approaches 0 of sine h on h is equal to 1. These are special limits that we have for trig. So that means that I'm going to have sine x multiplying this limit, and this limit from the identity we have it to be 0 plus cos x, and then this limit, the limit as h approaches 0 of sine h over h is just 1. It's an identity in limits involving trig, and that is times 1. Then finally I have 0 times sine x, which is 0 plus cos x, and the final answer is cos x. That means that anytime we differentiate sine x, we are going to get cos x. Alright, I'm going to go ahead and then do a second example. This time around I'm going to do it for f of x equals e to the power x. Let's do e to the power x. That is a exponential function. Alright, so f prime of x will be equal to the limit as x h approaches 0, of f of x plus h minus f of x all over h. Alright, so I'm going to have the limits as h approaches 0. Now f of x plus h, so wherever I see x, I'm going to substitute x plus h. So e to the power x plus h minus f of x, which is e to the power x all over h. Now with this particular one, I'm going to apply the law of indices here, right, to break it down. So the limit as h approaches 0. Now I'm going to have e to the power x times e to the power h. You remember the law of indices. If the exponent are the same, we add, if the bases are the same, we add the exponents. So since the exponents are being added, I can break it down into multiplication, then minus e to the power x all on h. For the sake of space, I'm going to continue from here. Then I'll now take the limit as h approaches 0 of, now look at something, I'm going to factor e to the power x out because each term has a common factor, which is e to the power x. So I'll factor e to the power x out, then I'm going to have e to the power h minus 1 all over h. Now since I'm taking the limit as h approaches 0, then any term without h can be treated as a constant. So the e to the power x that I have here, I'm going to factor it out. So I'm going to have e to the power x times the limit as h approaches 0 of e to the power h minus 1 over h. Now this is also a special limit. This is also a special limit. We have a special limit which says the limit as h approaches 0 of a to the power kh minus 1 over h is equal to k ln a. So you write the answer as k ln a. So when we consider this limit, we can see our k is 1, the coefficient of h is 1, and then our a is actually e. So we are going to have e to the power x, k is 1, so no need to write the 1, then ln e, and you know ln e is equal to 1, so finally the answer is e to the power x. Right, so when you differentiate the exponential function e to the power x, you are going to get e to the power x. You're definitely going to get the same thing. Now in the next example, I want us to look at a power function. So example 3, let's look at f of x equals e to the power x, where a is greater than 0. Alright, so f prime of x will be equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So this is going to be the limit as h approaches 0. Now wherever I see x, I'm going to replace that with x plus h. So the exponent will be x plus h minus a to the power x, which is f of x all over h. Here too, I'm going to do a similar thing as I did for the exponential function. This term, because the exponents are adding, I can separate it using the law of indices. So I'm going to have a to the power x times a to the power h minus a to the power x all over h. And then the common factor here is a to the power x, right? So I'm going to factor that out, a to the power x out, then I have a to the power h minus 1 all on h. For the sake of space, let me continue from here. So here too, since I am dealing with, I'm finding the limit as h approaches 0, it means that any term without h, I treat it as a constant and I can factor that one out. So I'm going to factor a to the power x out, then find the limit as h approaches 0 of a to the power h minus 1 all on h. Now this one represents the special limit I showed you in the previous. Let me show you quickly. This particular one, this particular limit, right? So we have gotten a similar one there. So let's compare to see. Now we can see that our k is 1. The coefficient of h is 1, and no need to multiply by 1. All right, so ln a, so we're going to have ln a. So anytime you take the derivative of a to the power x, you get your answer to be a to the power x times ln of a. So this is how we use differentiation by first principles to find the derivatives of some special functions. Now I need you to try these ones. So I have some few examples for you to try. F of x equals e to the power 2x. F of x equals cos x. Then f of x equals ln x. I need you to try these ones. So example 4, example 5, and then example 6. Try them and put your answers in the comment section, or you can send it to me via my email. Thank you for having me.